The sun, smooth and round and peaceful, except when it suddenly vomits radiation and plasma in random directions. These solar flares and coronal mass ejections, or CMES, can hit Earth and have serious consequences for humanity. How exactly do they work? How bad could they be? And can we prepare for them? Intro music. While the sun seems pretty solid, it's actually like a very hot ocean. So hot that it rips atoms into electrons and nuclei, all flowing around each other in a plasma. This plasma is pushed around and shaped by the sun's magnetic field, similar to how the sun's gravitational field reaches out to the planets and shapes their orbits. But magnetism is very different from gravity. Magnetism is one part of a dual force, electromagnetism. Electricity creates magnetic fields, and magnetic fields create electricity. On the sun, the plasma, made of electrically charged protons and electrons, creates a magnetic field as they move, and this magnetic field then shapes the flow of particles. They're stuck in a dynamic feedback loop called a dynamo, which keeps the sun's magnetic field alive. This magnetic field stores enormous amounts of energy and leaks out over the solar system. It carries with it a constant trickle of solar plasma, like a light rain, known as the solar wind, creating a sort of space weather. But it isn't always calm and smooth. As the sun's plasma churns and flows around itself, its magnetic field gets all kinked and twisted. This creates magnetic knots that build up enormous amounts of energy. When the magnetic knots break, like a tangle of springs exploding outwards, the sun can vomit plasma and other awful things into the solar system. These solar storms come in many types, like solar flares, a tidal wave of high-energy radiation. They race through the solar system at the speed of light, sweeping up protons in the solar wind, accelerating them into a high-speed solar proton storm. Then there are coronal mass ejections, which rip millions or billions of tons of plasma from the sun's atmosphere, catapulting it through the solar system at speeds of up to 9 million kilometers per hour. When these monsters hit us, nothing happens on Earth, while even smaller storms can damage satellites, affect radio communication, or be dangerous to astronauts. For people on the surface, space weather is harmless. Earth's atmosphere protects us from the worst effects of a solar flare by absorbing the blast of X-rays high up in the atmosphere well before it reaches the surface. The electrified plasma from a CME is deflected by the Earth's magnetic field, diverting the energy storm to the north and south poles, where energetic particles fall into the atmosphere, causing the atmosphere to glow and creating beautiful auroras. As with any sort of weather, most of the time, things are fine. Sometimes there are hurricanes, though, or, in the case of the sun, solar superstorms. And we know that they happen once or twice every century. If one were to happen today, we would first detect strong solar flares, a sort of flash before the much more dangerous thunder. The thunder is a CME, consisting of billions of tons of hot magnetic plasma that crosses the 150 million kilometers between the sun and Earth in less than a day. When it arrives, it causes a shock wave that violently compresses the Earth's magnetic field and transfers energy into the magnetosphere. But it can get worse. If the magnetic field of the CME is aligned to Earth's in just the right way, the two magnetic fields merge. As the magnetic cloud passes over Earth, it stretches the Earth's field into a long tail. Eventually, the energy stored in the tail becomes too much to contain. It snaps and explosively releases its energy towards Earth. A geomagnetic storm has begun. A few hundred years ago, nobody would have cared. This storm gushing over the Earth is not relevant for machines made out of meat and bones, but it's very relevant for machines made out of metal and wire. Remember the dynamo? Magnetism creates electric currents. Earth in the 21st century is covered in millions of kilometers of wires, transporting electricity and a complex grid of machines, like transformers, that make this transfer possible. A CME's energy can induce currents in our power grid that can either completely shut it down, or worse, destroy the transformer stations that keep our grid running. This has happened already, like when the Quebec power grid failed after a strong solar storm in 1989. But in general, our engineers know how to deal with these storms, and so we usually don't even notice. The last time a solar hurricane washed over Earth was in 1859. The Carrington event, the largest geomagnetic storms ever observed on Earth. Massive auroras occurred as far south as the Caribbean. In some places, they were so bright that people got up, thinking the sun was rising. Luckily, we only had one sort of modern technology: telegraph systems. They failed all over the world. It's impossible to predict the exact surface temperature on Gliese 667 cc. If the planet does have an Earth-like atmosphere, it would transfer heat and equalize temperatures across the entire planet with a pleasant 30 degrees Celsius, 86 degrees Fahrenheit, on the night side. Living on such a planet would be a much different experience. GJ 667 cc receives a faint, reddish light from its star. The other two stars, Gliese 667a and b, are located at a distance of about 230 astronomical units, much further than the distance between Pluto and the Sun, and outside the planetary system. However, the two other suns would still be seen as a pair of bright stars, visible in the daytime, and at night they would shine as bright as the full moon, and our sun would appear as a distant star. Unfortunately, the nearby red dwarf is known to emit flares or intense bursts of radiation and energetic particles up to 1,000 times stronger than flares on our sun. This could be problematic for any potential life on the surface of Gliese 667 cc, as the planet is located close to its flaring host star. And the strong magnetism of the red dwarf may cause star spots that can reduce the energy output of the star by up to 40% for months, which, combined with the lack of ultraviolet light emissions, would be another issue for the formation of life as we know it. Living on Gliese 667 cc would be nothing like what we're used to, also because of how massive it is. The higher mass of the exoplanet means different gravitational acceleration on its surface. This world is rocky, and so the gravitational acceleration would be up to 60% higher than what we experience on Earth. A person weighing 75 kilograms, 165 pounds on Earth, would weigh as much as 120 kilograms, 265 pounds, on Gliese 667 cc. In addition, a planet with higher mass can hold a more massive atmosphere, leading to higher atmospheric pressure at the planet's surface. In case it has an atmosphere similar to Earth's, the atmospheric pressure would only be a few times higher, but if the exoplanet has a Venus-like atmosphere, the pressure could be several hundred times greater, equivalent to the water pressure several kilometers deep in Earth's oceans. Despite its location in a habitable zone, Gliese 667 cc may not have the same conditions as Earth. Life forms on Gliese 667 cc may have to adapt to fluctuating and low light, a potentially high atmospheric pressure, and frequent flares. But this doesn't mean life cannot form on such a world. We've already seen examples of remarkable life adaptability on Earth. The two other potentially habitable planets are almost identical. Gliese 667c e, mass 2.7 Earths, radius 1.45 times Earth, and Gliese 667 cf, mass 2.7 Earths, radius 1.45 times Earth. 1.45 times Earth are both located farther out from their parent star, meaning they receive less energy. This could make them too cold to support life as we know it. But, unlike with GJ667cc, having a thick atmosphere would be beneficial for potential life on these planets, as it would trap heat and maintain favorable temperature conditions. Spotting 3 such worlds in the habitable zone of the same planetary system is extremely rare, but 4 is almost unthinkable. According to one study, 5 planets in the Gliese 667c system are estimated to receive solar radiation, ranging from 20 to 200% of the current exposure of Earth to the Sun, which makes them all candidates for potential habitability. But there are other factors in play. Scientists have determined that for a planet with a mass equal to Earth, the habitable zone around Gliese 667c has 2 boundaries. The inner boundary lies between 0.095 and 0.126 astronomical units from the star, while the outer boundary lies between 0.241 and 0.251 astronomical units. Any planet orbiting within these distances from star C may be able to sustain life, as it would have the right conditions for liquid water to exist on its surface. If a planet is too close to its star, the heat will cause water to turn into vapor and escape, making the planet uninhabitable. This happens because water vapor is a greenhouse gas, which can trap heat and cause temperatures to rise to intolerable levels. Only the planets at the inner edge of the habitable zone with a larger mass are more resistant to the moist greenhouse effect. On the other hand, if a planet is too far away from its star, like the outermost Gliese 667g, it risks being covered in ice, while gases like CO2 can warm the planet and prevent this. Too much CO2 can actually cool the planet down by reflecting light away. So there's a limit to how much CO2 can help warm a planet. In 2013, astronomers made an announcement that Gliese 667c has a minimum of 6 planets, and there's a possibility of a 7th planet designated as GJ667ch. Although highly controversial, the exoplanet could be the smallest one found so far around star C, with a mass of at least 1.1 times that of Earth, located just between the planets C and B.